Okay, this is a change of subject, right? This is going back to quadratics. This is a part of, we did some quadratics. We did them in terms of factoring, a little bit of solving equations, but we didn't do anything with the graph. And it's in the curriculum, and it's not in the Algebra 2 curriculum, so if you don't see it here, you pretty much would never see it. So that's why we're doing it. So in this case today, we're starting with a quadratic, which is only possibly being multiplied by a number and maybe having a number added or subtracted after. So by quadratic function, we mean any kind of function which the highest power of x is 2. These are all examples of quadratic functions, right? Because in every case, you can see the x squared. Maybe the only one you don't quite see the x squared is this one here, right? But you could tell if I take that x minus 3 and I square it, that would be x minus 3 times x minus 3, and the highest power of x would still be a 2. So in any which way you see it, all of these are considered to be quadratic functions. And we know that the shape of the graph of a quadratic function is a parabola, right? It's a kind of looks like a U. So this is my best way to copy this right now. So this is the beginning of what we start calling parent functions. When you take a certain kind of function and you just show the simplest example of it. In fact, this one here, it says the most basic quadratic function is y equals x squared. And of course, it's a parabola. But what's different about it for sure is that it's always the origin is the bottom of the U, and you call that point the vertex. Okay, a parabola is symmetric, means it's the same on one side as it is on the other. And if I draw a line straight up and down through the vertex, that is called the axis of symmetry, because it's the same on one side as it is the other. Okay. Now, the thing about it being symmetric is, you know that if there's a point 1 to the right of the axis of symmetry, then there's got to be a point which is 1 to the left, right? If there's a point which is 2 to the right, there's got to be a point which is 2 to the left. It has to be exactly symmetric. Okay. So those are 2 vocabulary words here. Well, actually 3. Parent function just means the basic example of that function. Edric, Ty. Okay. And vertex and axis of symmetry. There you go. Three vocabulary words. Okay, so now we're going to look at what happens to change that graph. So what I've got in every one of these graphs is I'm showing the parent function y equals x squared. And I'm using a table of values. In every one of these cases, the x values are -2 to +2. Right? And the x squared is the parent function, y equals x squared. You could see the graph. The best I could sketch it anyway. Now we want to know what's going to happen to that graph if I end up multiplying by 3. Well, what happens in my table of values, right? If I take that x squared and I multiply it times 3, what do all the y values become? 3 times 4, 12. 3 times 1, 3. 0, 3, 12. Okay, if I graph those the best I can, right, I got -2, 12 would be like off the chart, somewhere up here. -1, 3 is here. 0, 0 is still on the graph. And I got 1, 3, and 2, 12. So again, somewhere way up there. And if I try to do my best job at sketching that, you know, what does it look like it did to the graph by multiplying it by number 3? It kind of made it a little skinnier, and really what it's doing is it's making it go up faster, right? So for every y value, it's going up by a factor of 3. I just multiplied 4 times 3, right? So every one of our y values end up being 3 times what they were in the first place. So of course it's going to make it go up faster. Okay. Now what do you think is going to happen if I multiply times 1/4? Okay, now I'm multiplying every one of these x squared values by 1/4, which means I've got 1, 1/4, 0, 1/4, and 1. So let me graph those values. So at -2, 1. At -1, 1/4. 0, 0, 1/4, and 1. Now I can draw my parabola. What does that look like it did to the graph by multiplying by 1/4? Okay, you could call it wider. It's making it go up slower, right? The values are all 1/4 of what they would have been in the past. Okay, so we have new vocabulary words for that. If the number you're multiplying by is greater than 1, you're calling it a stretch. It's stretching the graph this way. If the number you're multiplying by is less than 1, that's called a shrink. It's kind of flattening it out, making it look kind of wider, right? So those are two words, stretch and shrink. If that number in front of the x squared is greater than 1, stretch. If it's less than 1, shrink. Okay, now what happens if I put a negative in front of the x squared? What is it going to do to all of those x squared values here if I put a negative? They're all going to go negative, right? -1, 0, -1, -4. If I graph those, right, now I'm here, 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 and here. Okay, and I've sketched the curve. Right, what does it look like it did to the graph? It turned it upside down. Okay, well, we've got vocabulary for that too. It's flipped. If the a is less than 0, it's a flip, right? Sometimes we just say it's flipped. Sometimes in the textbook, the real proper way to say it is, it's reflected in the x-axis. But if you just say flipped, that's okay too, right? So you could say it's flipped across the x-axis, reflected in the x-axis, or just flipped. So if this number here is less than 0, okay, now what if it was like y equals -2x squared? Would you say it's a stretch or a shrink? So, you know, what we said on that slide 3 before here, if the a is greater than 1, it's a stretch. If it's less than 1, it's a shrink. It's really, to be fair, it's absolute values. And the way I like to think of it is like this. Just separate the minus sign from the number 2. Right? If I just look at the minus by itself, I'm going to say, well, that's the flip. And that 2 by itself, that's the stretch. Now, the truth is it's being stretched down. Okay. But, I mean, if you look at it, say, well, -2, isn't that less than 1? Shouldn't that be a shrink? And the answer is no, it's not a shrink. It's still a stretch. Okay, now let's see what happens if we add a number after the x squared. What does it do to all these x squared values if I add 5? How about they add 5? 9, 6, 5, 6, and 9. So if I plot those, again, I'm going to be a little off the chart here. 9, 6, 5, 6, and 9. If I sketch that, what does it look like it did to the graph by adding 5? It looked like it moved it up, right? So adding a number after the function moves it up. Yeah, well, we don't really have to times it by 1 because 1 times anything is the same thing, right? But you could have a number multiplying and a number adding. Okay, how about, what do you think will happen if I subtract 4 after the function? It's going to go down 4, right? These numbers are going to become 0, -3, -4, -3, and 0. Okay, so what does it look like it did to the graph of the function because we subtracted a number? down. Mike, wait a few, right? We're almost done. Okay, so it looks like by subtracting 4, it moved the whole graph down 4. So if you add a constant after the function, if that number is bigger than 0, it shifts it up. If it's less than 0, it shifts it down. It's a vertical shift. Now there's going to be one more kind of shift that's not today, but that's how do you shift it left and right? And you shift it left and right if there's an x term. Like here we just have an x squared term and a constant. But if I had like a x squared plus 2x plus 4, the presence of that term there means it's not going to be in the middle. It's going to be shifted left or right. Okay, so if you're just adding a constant, that's a vertical shift. Plus means up. Minus means down. Again, and what was the effect of the A? Multiplying. What are the different things it can do to the graph? It can shrink it. It can stretch it. Or it can flip it. Right? Stretch, shrink, or flip. So let's look at these three right here and just describe what are the things that are going on in this, right? What is going on with that 3? These are called transformations, the general term. So multiplying times 3 is a stretch. How about subtracting 6? How does that change the graph? Down, right? How about the minus in front of the negative 5x squared there? No. A minus does what? It's a flip, right? A 5 does what? Stretch. A plus after the function? Up. Okay, how about multiplying it times 3/4? That's a number less than 1. That's a shrink. Okay, how about subtracting 2 after the function? Down. Okay. So that is that. So again, work on this in class now. The 7, 11, 17, and 19, make a table of values, find the values, plot the points, sketch the curve. The 24 through 32, it says to graph, but you don't have to graph. Just describe what would go on. Just describe those 3 or 4 things that we just did.